Let's talk about the quantum mechanic model of the atom. We know now that Bohr's model explained the emission spectrum of hydrogen, but it didn't always explain the emission spectrum that was viewed by other elements with more than one electron. So that brings us to the quantum mechanic model in and around the 1920s. And I'm going to touch a little bit on Heisenberg, de Broglie, and Schrödinger and how they have contributed to our current thinking of the atom. So first we need to know what is an electron, okay? This is what we're trying to figure out. What is it? We want to know where it is, and we don't need to necessarily know the whole mathematics behind its location, but we should at least be able to address some of these questions. So sometimes the electron is treated as a wave, and sometimes it is treated like a particle, much like light. Sometimes we call it a wavicle because it's a particle and it's a wave.
In his doctoral dissertation in 1924, Louis de Broglie put forward a simple idea that significantly advanced the understanding of the extremely tiny. A quantum leap forward, you might say. Since Einstein and Planck and Compton had firmly established that light could have the characteristics of both a wave and a particle, de Broglie suggested that matter particles, protons, electrons, atoms, billiard balls, could sometimes act like waves. And when this idea was applied to Bohr's atom, it answered many questions. First, the allowed orbits had to be exact multiples of the wavelengths calculated for the electrons. Other orbits produced destructive interference of the waves, and soon the electrons couldn't exist there. So the circumference of the orbit must equal the wavelength, or twice the wavelength, or 3 times the wavelength, or for that matter, any multiple of the wavelength. Second, these orbits weren't really orbits in the traditional sense. These electrons didn't travel around the nucleus in a circle. Rather, they took the form of a standing wave that surrounded the nucleus entirely. The exact position and momentum of the electron particle could not be specified at any given instant.
So electrons display properties of both waves and particles. To think of them as a particle is easy because they have a small amount of mass, and there is evidence that they have wave-like behavior. In a sense, they're neither a particle nor a wave in an absolute sense, but only exhibit wave or particle properties depending on the experiment being performed.
And here we are, the granddaddy of all quantum weirdness, the infamous double-slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, 2 bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits and it goes through neither. And it goes through just one and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange, never world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
So lots of good information there. So you can see that based on the experimentation being performed, the electron can sometimes behave as a particle or it can behave as a wave. So de Broglie proposed that the electron has this wave-particle duality, and that he actually has a formula where the wavelength is equal to Planck's constant divided by the mass times the velocity. And again, we're not going to look at the mathematics behind it, but please make sure that you download the information sheet that I have to sort of give you some notes to go by. And then we've got Heisenberg's uncertainty principle. So basically, he is stating that we cannot know both the position and the momentum of a particle at a given time. So if you know where the particle is, then you don't actually know where it's going. Think of yourself in, a pitch black room, and there are a bunch of soccer balls, and you enter that room and you know that there are balls there, and you kick one. So at that moment in time, you knew where that soccer ball was, but once it's been kicked in that dark room, you don't know where it now has gone. So you can't know both the position and the momentum of a particle at a given time.
A true giant of quantum revolution was Werner Heisenberg. And from the vagueness of positions of electrons in de Broglie's standing wave orbits, he drew a tremendous insight which he stated like this: the more precisely the position is determined, the less precisely the momentum is known, and vice versa. And while it may sound like a bunch of gobbledygook, it was the insight necessary to understand how an object can be both a particle and a wave. This single statement led to the understanding that subatomic particles can disappear and reappear in another place. And they can do this without existing in the intervening space. When an electron is trapped inside an atom, the places it can disappear and reappear include specific locations around the nucleus. And that makes it look like a shell. Basic particles can also be in more than one place at a time, if the time is brief enough. An electron can travel from here to there along all possible paths simultaneously. And even more astounding, these particles can appear out of the nothingness of space, exist for an extremely brief instant, and then disappear. Scientists call them virtual particles. They may be virtual, but they can have very real effects. All this jumping around makes particle description so inexact. But then existence itself is inexact at these tiny scales. The question is often asked, what is it that is waving when a particle is described as a wave? And after a lot of hem-hawing around the issue, the right answer is, existence is waving. The particle is jumping around, coming into and out of existence. And those places where the wave crests are maximal are the places where the particle materializes, most of the time. While the places where the crests are minimum are the places the particle avoids. The wave is a map of the particle's existence. And as the wave changes, the particle changes as well. While all important ideas necessary for quantum theory were established before him, it fell to the genius of Erwin Schrödinger to develop the equation that correctly describes the motion and behavior of all things this tiny. While Bohr and de Broglie managed to describe the hydrogen atom, Schrödinger's equation was able to describe hydrogen with the same detail. And then it could go far beyond. It manages to account not only for the hydrogen atom, but it describes nothing less than all the atoms and all the elements in the universe. Schrödinger's quantum mechanics explains every element in the periodic table of the elements. The solution to Schrödinger's equation, called the wave function, is a fantastically accurate description of the real world.
Schrödinger was able to mathematically describe the probability distributions of where an electron might be found. And his mathematics is like astounding. So this would be his equation, and each of these symbols represents, a certain variable within the equation. And from that, he could actually deduce where the probability of finding an electron in a given space in and around the nucleus. And this takes us to what is known as the quantum numbers. And these quantum numbers will enable us to essentially devise an address for each and every electron in an atom. So the uncertainty principle of Heisenberg does not make it impossible for us to figure out where an electron is. We can base it on probability and how much energy is associated with that particular electron. So what we're going to talk about moving forward is where these electrons are located, and they are no longer located in shells per se, but more so in regions of space that we call electron clouds or electron orbitals. And these orbitals, do not confuse with orbits, are regions of space where the electron is sort of whirling about billions of times in a second, and they are moving in random patterns. And when we plot a 3D map of where a particular electron is going to be, we will see that it creates a space that has a certain shape associated with it. So for instance, if you were to take hydrogen and map the one electron of hydrogen over a period of time, you would notice that every one of these dots represents where the electron would show up over a period of time. And we notice that there's a high probability that it could be found here or here or here or here or here. And this seems to take on a particular shape. The location of the electron, remember, depends on how much energy the electron has. The closer the electron is to the nucleus, the lower amount of energy it has, and the electrons that are farther from the nucleus have more energy associated with them. So again, here would be a map, and this is what is considered to be the 1s orbital. So 1 meaning it is in the first energy level, and S standing for what we refer to as an S-shaped orbital or a sphere-shaped orbital. So the electron is most probably found somewhere in and around here because it's more dense, but at any given moment, it could be there, it could be there, it could be there, it could be there. If we know its position, we don't know where it's going. If we know where it's going, then we don't actually know its position. So again, we take that map and we sort of put it into a shape that we would consider to be this cloud region or orbital, and that would be the S-shaped orbital. So the quantum mechanic model tells us the electrons are located in specific energy levels. There's no exact path around the nucleus that it is taking, and it just estimates the probability of finding an electron in a certain position. So here are some of the unique orbitals that we are going to be learning about when we talk about the 4 quantum numbers. This is pretty neat to see. And you'll see that these 3-dimensional shapes, we have an X, Y, and Z axes, and an electron can be found in that region of space, which we would consider to be the first energy level. And the first energy level has an S-shaped orbital. Now, P-shaped orbitals are sort of dumbbell in shape, so they're multiple lobed. So we have a double lobe on the Z, the Y, and the X axes. Any 2 electrons could be found on that axis, on the other axes, and so forth. There are what we refer to as D-shaped orbitals. They are multiple lobed. So again, these are just clouds or regions of space that you would have the probability of finding an electron in that region of space. As we keep adding more and more electrons to an element, as you get higher up, let's say, you've got sodium and it's got 11 electrons. Well, you need to account for the regions of space where they would be located. And so all of these regions of space have been mapped out and their relative shapes. So kind of neat. We'll be learning about that as we move forward. So there we have it, going from Dalton to Thomson to Rutherford to Bohr's to Schrodinger's electron cloud model, or we call it the quantum mechanic model of the atom.